Welcome back to another explainer. Today, we are decoding a really fascinating IEEE research paper, all about using mathematical chaos to protect the video streams we watch every single day. I mean, it sounds a bit like science fiction, right? Using actual chaos to create order and security. But as our digital world just keeps expanding, saving our video streams from unauthorized users has become an absolute necessity. So today, we're unpacking a groundbreaking study that proposes a highly efficient, entirely new encryption technique designed specifically for advanced H.264 video coding. Okay, let's take a quick look at our roadmap for today. We're going to cover 1. The video security problem. 2. How H.264 compression works. 3. Encryption using chaos maps. 4. The art of steganography. And finally, 5. Testing the encryption results.
All right, diving into section 1, the video security problem. Basically, our modern digital conflict.
So here is the million-dollar question we're facing. How do you actually protect a video stream without slowing it down? We have a massive vulnerability right now when streaming video, mostly because we have to protect huge, I mean literally massive, amounts of multimedia data instantly, in real time, all without causing a single drop of lag for the viewer. Think about it for a second. When you click play on a 4K stream, you expect instant gratification, right? Any delay or buffering completely ruins the experience. But all that data traveling through the network is incredibly vulnerable to hacking if it's just left exposed.
Now, you might be wondering, why don't we just use the security we already have? Well, standard cryptography, like the Advanced Encryption Standard, AES, or DES, they are highly secure for sure, but they carry a heavy computational burden. Actually, scratch that. They aren't just heavy, they're computationally exhausting for continuous streams. They were built to lock down static files, not continuously flowing high-def visual data. If you try to force real-time H.264 video through these traditional algorithms, it just completely ruins the speed. It takes way too much processing power, and that leads to unacceptable lag. The researchers behind this paper realized we needed a completely different approach.
Moving right along to Section 2, how H.264 compression works. This is essentially the canvas we're working on. To really get this, think of H.264 compression kind of like breaking a massive video file into tiny little puzzle pieces. It's a widely used standard because it gives us so much flexibility with storing and transferring data. The encoding happens in 3 main steps. First, you have spatial and temporal prediction, also known as intra and inner prediction. Second, mathematically transforming and quantizing that residual data. And third, locking the whole shebang into a super tight bit stream using entropy encoding. It's a brilliant process that just strips away any redundant visual information. And looking at the actual schematic right from the research paper, you can clearly see the entire flow from a raw video source straight down to a compressed transmittable file. Up on the top, the encode process breaks the frames down, runs those prediction and transform steps we just talked about, and pushes out that compressed bit stream. Down on the bottom is the exact mirror image, the decoding process that your TV or phone runs to rebuild the video for your screen. To encrypt this effectively, our security measure has to seamlessly integrate into this exact flow without breaking it.
Now, zooming in on a micro level, this prediction phase is honestly fascinating. By analyzing neighboring pixels and sorting them into these little 4x4 macro block grids, or puzzle pieces, the standard predicts and removes visual redundancies. What we're looking at here are the 9 different prediction modes for the luminance, or basically the brightness, of an intraframe. The encoder looks at the surrounding pixels and essentially just guesses what the next block should look like based on these directional modes. It saves an incredible amount of data.
All right, part 3, encryption using chaos maps. This is where things get incredibly unpredictable.
Enter our unexpected hero, the chaos map. In math, a chaos map is a nonlinear dynamic system where the tiniest, almost microscopic change in a starting seed creates a radically different and entirely unpredictable outcome. It has this amazing randomness-like behavior, highly unstable periodic orbits, and extreme sensitivity. Because of these specific traits, the parameters of a chaotic map can act as a phenomenal, lightweight encryption key. It's complex enough to be mathematically secure, but fast enough to not bog down our video encoding process. Let's look at one really cool example tested by the researchers, the Decoding map. As it's graphed out here, it visually represents these complex difference differential equations, acting as a totally tangled, randomized digital key. Originally introduced back in 1987, it graphs into this incredibly dense web. If you use the coordinates of this map to scramble the luminance components of a video frame, it becomes practically impossible for a hacker to guess the original state without knowing the exact starting parameters. We also have the Henon map,
which serves as this beautiful, almost abstract mathematical fingerprint. It proves that chaos actually has enough underlying structure to act as a flawless cipher for our data. The Henon map relies on two-dimensional area-preserving equations. The shape you're seeing is the mapping of those equations over countless iterations. From a distance, it kind of looks organized. But mathematically, the values jump around completely unpredictably, giving us a highly secure stream of values that can mask the video data completely.
Which brings us to part 4, the art of steganography, literally hiding in plain sight. So here is the absolute game changer. The difference is crucial here. Cryptography attracts hackers because it looks like a scrambled locked file. It's essentially waving a giant red flag that says, hey, valuable data right here. But steganography? It operates invisibly. It's the art of concealing a message entirely. In this proposed system, researchers actually conceal a low-resolution video frame directly inside a high-resolution one. It's exactly like building a secret compartment inside a digital briefcase. A hacker might look at the file, see a totally normal high-res video, and be completely unaware that heavily encrypted confidential data is hiding right there beneath the surface pixels.
Finally, Section 5, testing the encryption results. Time to actually prove the math.
The researchers didn't just guess that this worked. They ruthlessly tested it using MATLAB software, evaluating their chaos maps against strict performance metrics. They looked at the mean squared error, or MSE, to see the exact numerical difference between original and decrypted frames. They measured the peak signal-to-noise ratio, PSNR, to check for image degradation. And they tracked the number of pixels change rate, the NPCR, to prove that if a hacker changed even one single pixel of the encrypted data, the whole outcome would radically alter, totally ruining the hack.
And after putting the Ikeda, Henon, and other models through the absolute ringer, the study revealed a clear winner. The logistic chaotic map achieved the best overall results for securing real-time compressed H.264 video. It hit that perfect sweet spot, maintaining absolute visual quality, keeping storage capacity low, resisting malicious attacks effortlessly, and, most importantly, executing the encryption without sacrificing the real-time speed of the stream. Chaos, beautifully harnessed, creates perfect security.
So that wraps up our explainer for today. But I want to leave you with this one final thought. If our daily video streams are now beginning to rely on the absolute unpredictability of mathematical chaos for protection, what invisible systems will be required to secure our digital lives in the future? As our data gets faster and increasingly complex, our methods of hiding and securing it are clearly going to have to become even more brilliantly chaotic. Think about that the next time you hit play. Until next time, keep learning.